Hello, today we will have the first lecture of our Calculus 1 course. We will cover two very important topics, tangents and velocities. These concepts are very important because they will help introduce derivatives and their applications. Please like the video and subscribe to our channel. First of all, we start by giving the definition of the term tangent. The word tangent is derived from the Latin word tangens, which means touching. Thus a tangent to a curve is a line that touches the curve. In other words, a tangent line should have the same direction as the curve at the point of contact. For a circle, we could simply follow Euclid and say that a tangent is a line that intersects the circle once and only once, as in the following figure. For more complicated curves this definition is inadequate. The following figure shows two lines L and T passing through a point P on a curve C. The line L intersects C only once, but it certainly does not look like what we think of as a tangent. The line T, on the other hand, looks like a tangent but it intersects C twice. Let us look at this first example. Find an equation of the tangent line to the parabola at the point P, 1, 1. We will be able to find an equation of the tangent line T as soon as we know its slope m. The difficulty is that we know only one point, P, on T, whereas we need 2 points to compute the slope. But observe that we can compute an approximation to m by choosing a nearby point Q, with x-coordinate x and y-coordinate x square, on the parabola, as in the figure, and computing the slope mpq of the secant line pq. A secant line, from the Latin word secans, meaning cutting, is a line that cuts, intersects, a curve more than once. We choose x is not equal to 1 so that q is not equal to p. Then for instance, for the point q, with x-coordinate 1.5 and y-coordinate 2.25, the slope of the secant line is the fraction 2.25 minus 1, over 1.5 minus 1, which is 2.5. The tables below show the values of mpq for several values of x close to 1. The closer q is to p, the closer x is to 1, and it appears from the tables, the closer the slope mpq is to 2. This suggests that the slope of the tangent line T should be m equals 2. We say that the slope of the tangent line is the limit of the slopes of the secant lines, and we express this symbolically by writing, the limit as p goes to q of mpq equals m. In fact, the limit as x goes to 1 of x square minus 1, over x minus 1 is equal to 2. Assuming that the slope of the tangent line is indeed 2, we use the point slope form of the equation of a line y minus y1 equals m times x minus x1 to write the equation of the tangent line through the point P, 1, 1, as y minus 1 equals 2 times x minus 1 or y equals 2x minus 1. The three figures illustrate the limiting process that occurs in this example as q approaches P from the right. As q approaches P along the parabola, the corresponding secant lines rotate about P and approach the tangent line T. Now, let us talk about another seminal problem that will help us introduce the concepts of limit and derivative. The problem we will briefly introduce is the velocity problem. We start with the classical freely falling body problem. Suppose that a ball is dropped from the upper observation deck of the CN Tower in Toronto, 450 meters above the ground. Find the velocity of the ball after 5 seconds. Through experiments carried out 4 centuries ago, Galileo discovered that the distance fallen by any freely falling body is proportional to the square of the time it has been falling. This model for free fall neglects air resistance. If the distance fallen after t seconds is denoted by s, t, and measured in meters, then Galileo's law is expressed by the equation, s of t equals 4.9 times t square. The difficulty in finding the velocity after 5 seconds is that we are dealing with a single instant of time, t equals 5, so no time interval is involved. However, we can approximate the desired quantity by computing the average velocity over the brief time interval of 1/10 of a second, from t equals 5 to t equals 5.1, as a matter of fact, the average velocity is equal to the quotient of the change in position or the distance traveled over the time elapsed. In this case, it is s of 5.1 minus s of 5, divided by 0.1. Now, when we plug in the values, we have 4.9 times 5.1 squares, minus 4.9 times 5 squares, divided by 0.1. So the average velocity is 49.49 meters per second. The following table shows the results of similar calculations of the average velocity over successively smaller time periods. We can see that over the time period from t equals 5 to t equals 5.1, the average velocity is 49.49. Over the time interval from t equals 5 to t equals 5.05, the average velocity is 49.245. Finally, over the time interval from t equals 5 to t equals 5.01, the average velocity is 49.049. It appears that as we shorten the time period, the average velocity is becoming closer to 49 meters per second. The instantaneous velocity when t equals 5 is defined to be the limiting value of these average velocities over shorter and shorter time periods that start at t equals 5. Consequently, it appears that the instantaneous velocity after 5 seconds is v equals 49 meters per second. On this, we end this lecture. Thanks for watching the video. Please do not forget to like the video and subscribe to our channel. We have an extensive collection of mathematics lecture notes covering all sequences of calculus, college algebra, discrete mathematics, and probability. Thanks.